The structural integrity of any computer network rests upon the mechanism of data egress, a process fundamentally governed by the default gateway. Local area networks are logically closed. Devices on the same subnet communicate directly, but without a configured gateway, they are trapped within the local broadcast domain, regardless of internal connectivity. The default gateway is the intersection point between Layer 2 hardware delivery and Layer 3 routing logic. Proficiency at this intersection allows an engineer to build the resilient egress points required by enterprise data centers. This technical scaling, from simple connectivity to advanced cluster design, mirrors the professional progression from the CCNA to the CCNP. Escaping the local subnet requires precise binary logic, not just the assignment of an IP address. The decision to forward a packet to the gateway is the result of a precise logic operation known as bitwise prefix matching. The host compares the destination IP with its own subnet mask using a bitwise AND operation. This process strips the host portion of the address to reveal the network prefix. If the resulting prefix matches the host's own, the destination is on link. The data can be sent directly to the local neighbor. If the prefixes do not match, the destination is off link. The host must then consult its internal routing table. The host scans its routing table for the most specific entry that matches the destination address. At the bottom of the table is the gateway of last resort, identified by the 0.0.0.0/0 prefix. This catch-all route handles any packet that lacks a specific matching entry in the table. Layer 3 logic identifies where the exit door is logically, but a host cannot physically transmit data to an IP address without a Layer 2 hardware identity. Physical transmission requires a Media Access Control, or MAC, address. The host first checks its internal address resolution protocol cache for an existing mapping of the gateway's IP to a MAC address. If the mapping is missing, the host initiates an ARP request. This is a broadcast message sent to every node on the segment, asking for the gateway's hardware ID. The router recognizes its own IP and responds directly with its specific MAC address. The host then encapsulates the IP packet inside an Ethernet frame, using the router's MAC address as the destination. The router receives this frame, de-encapsulates it, and consults its own routing table to determine the next internet hop. While encapsulation bridges the logical to the physical, routing all egress through a single piece of hardware creates a fatal single point of failure. Relying on a single physical router is an unacceptable risk in an enterprise environment. If that hardware fails, the entire attached subnet loses external communication. Engineers implement first-hop redundancy protocols, or FHRPs, to decouple the gateway from individual physical devices. These protocols allow multiple routers to share a virtual IP and MAC address, presenting the appearance of a single gateway to client devices. Cisco's HSRP and the open standard VRRP elect one active router to forward packets, while a standby router monitors the connection via multicast hello packets. If the active router stops responding, the standby router takes over the virtual address. Active standby redundancy protects the network, but it leaves secondary hardware idle, which limits the available bandwidth of the cluster. Efficient use of hardware requires load balancing, which is managed through the Cisco iOS command line interface. In HSRP, engineers manipulate priority values to ensure a specific router becomes active. They also use the preempt command, which allows a recovered router to reclaim its active status after a failure. For active-active load distribution, Cisco developed the Gateway Load Balancing Protocol, or GLBP. An active virtual gateway manages the distribution of distinct virtual MAC addresses to multiple active virtual forwarders within the group. Using a round-robin algorithm, the AVG responds to ARP requests by cycling through the available MACs, splitting host traffic across up to 4 physical routers. Transitioning from a single exit door to a GLBP cluster marks the shift from basic configuration to enterprise architectural optimization. This technical progression mirrors the path from the CCNA to the NCORE exam. The CCNA focuses on single-area OSPF and static routes. The CCNP NRC concentration requires troubleshooting multi-area protocols and route redistribution. The CCNA validates foundational knowledge of how protocols function, while the CCNP tests the ability to optimize and repair complex topologies. This expertise results in a salary premium of up to 25% for CCNP-certified professionals. Corporate investment is driven by high-demand specializations like advanced routing and network automation. A senior architect's priority is designing redundant clusters that maintain uptime through physical hardware failures. In February 2026, Cisco will overhaul its certification portfolio to reflect current data center requirements. This overhaul unifies the previously separate DevNet and CyberOps tracks into the main CCNA and CCNP hierarchy, incorporating security and automation into the core routing curriculum. Modern gateway management now requires AI-ready networking skills and infrastructure as code proficiency. Candidates should prioritize high-fidelity labs like GNS3 to actively internalize how the command line behaves during unpredictable physical failure states. Study efforts must prioritize troubleshooting, focusing on why protocols fail over simple configuration steps. By integrating automation skills with foundational egress architecture, engineers gain the specific competencies required to navigate the 2026 certification framework.